So for today's lesson, we're going to be looking at matrices, more specifically using the matrix method to solve simultaneous equations. So at the end of today's lesson, we should be able to write pairs of simultaneous equations. We should be able to rewrite these simultaneous equations in matrix form, and we want to be able to solve these simultaneous equations using a matrix method. So let's get right into it. Now, to explain a little bit more of what simultaneous equations are, we're going to use a very simple example. So the 4-H club at your school is having a cake sale. You bought 2 donuts and a bottle of water. For your purchase, you paid $260. We are to write an equation using the information above, and we are also to solve the equation to determine the cost of a bottle of water and a donut. So to do this, the first thing that we're going to do, we're going to let the cost of 1 donut be equal to D, and we're also going to let the cost of 1 bottle of water be equal to W. All right, now remember, we had 2 donuts and 1 bottle of water. So to write our equation, it's going to be 2D plus W is equal to 260. Next, we're asked to solve this equation to determine the cost of a bottle of water or the cost of 1 donut. So let's see if we can do that now. So first we're going to transpose. So in this case, I'm going to try to see if I can find the cost of 1 donut. So I transpose my W to get 2D is equal to 260 minus W. And then I divide both sides through by 2 to get D is equal to 260 minus W all over 2. I am not able to find the cost of the donut at this point in time. Let's see if we can find the cost of a bottle of water. Now I transpose 2D to get W is equal to 260 minus 2D. And here, as you can see also, I am still unable to find the cost of the bottle of water or the donut. It means that I'm going to need some more information. So let's see if we can get some more information to help us with this problem. Now, from the same 4-H sale, Tyrone bought 3 bottles of water and he also bought 3 donuts. He paid $480 for these items. We are to write an equation to represent this information above. All right, now let us remember we used D to represent the cost of 1 donut and W to represent the cost of 1 bottle of water. Are you guys able to tell me what you think the equation is going to look like? If you said 3D plus 3W is equal to 480, then you are correct. Now we have a pair of equations which reads 2D plus W is equal to 260, and we have 3D plus 3W is equal to 480. What we have here is what we call a simultaneous equation. And a simultaneous equation is really a group of 2 or more line equations that we're going to be solving together, with each equation having at least 2 variables. Now, there are many ways in which we can solve simultaneous equations. We have the elimination method. We also have the substitution method. We have what we call the graphical method, and we have matrix methods that we can use to solve our simultaneous equations. But for today, we are going to be focusing on the matrix methods to solve simultaneous equations. Now, to solve simultaneous equations using matrix methods, there are basically 3 simple steps that we are going to be taking in order to solve simultaneous equations. The first thing that we are going to do, we want to rewrite the simultaneous equations in matrix form. And in matrix form, it is given as matrix A being multiplied by matrix X, which gives us a matrix B. After we've done that, we want to make x the subject of the formula, after which we are going to simplify the equation from step 2 for the values of our variables. Now, just let's take a quick look at our information that we've gathered earlier and our simultaneous equations that we have written. So we have 2d plus w is equal to $260, and we have 3d plus 2w is equal to $480. Now, what we want to do, we want to be able to rewrite this as a matrix equation in the form ax is equal to b. So what we're going to do, we are going to look at each side of the equation. Now, the first thing that we want to note is that 2d plus w equal 260 is one equation. 3d plus 3w equal 480 is also another equation. And we are now going to combine these two in order to get our equation in the matrix form. Now, before we do that, we are going to take a short break. So before we get to our break, let us just review what it is that we've done so far. So far, we know that we have what we call systems of linear equations, which we call simultaneous equations. These equations basically have two line equations. They are a pair of equations, with each equation having at least two variables. We are discussing CSEC math, more specifically, matrix simultaneous equations. Now, just for the viewers, I hope that all my CSEC students from Yallas High School, from Port Antonio High School, from Fair Prospect High School, I hope you are all watching. And from my alma mater also, Excelsior High School, I hope you are watching this lesson, and I really hope that you're learning. Now, so far we've established what a simultaneous equation is. And our simultaneous equation is really a pair of equations with each equation having at least two variables. Now, ultimately, at the end of this lesson, remember we said that we wanted to write these equations as matrix equations and then solve them using matrix methods. So ultimately, we want to put it in the form ax is equal to b first. Now, just as with any professional, say even Usain Bolt, before he was able to run as fast as he could, there are things that he needed to do in order to reach where he was. When he's a baby, he creeped and then he learned to walk and then run and then train to be faster. We're going to be taking the same approach. So our first baby step is going to be rewriting this equation in matrix form. Now, if we realize, and we're going to start with, I'm going to start with my right hand side. We have $260 and 480. Now, if I should put this in a matrix, what it will be is a column matrix, because we have 1, 2 rows and only one column. So this is going to be a column matrix, 260, 480. And then on my left-hand side, I need an equal matrix, a matrix with one column and 2 rows. Good. So our first row is going to be 2d plus w, and our second row is going to be 3d plus 3w. That's the first step that we're going to take in order to get to our ax equal b. So here we have 2d plus w being equal to $260. We have 3d plus 3w being equal to $480. All right, so let's get back to this presentation. All right, and that's what you would see on your screen now. 2d plus w equal to 260, and 3d plus 3w equal to 480. And that's our first step in getting it into matrix form. All right. Okay, so what we're now going to also do, we are going to our second baby step, we're going to review matrix multiplication. Now, in order to multiply a 2 by 2 matrix by a 2 by 1, we are going to first get this color coded here. Nice. And then we're going to start by having, no, before we even go there, in the last lesson, we reviewed the multiplication of matrix. And remember, when we're multiplying matrix, it is the row multiplied by the column. So we'll multiply elements in rows across elements in the adjacent matrix column. All right? After which, we do that step by step, and then we'll have our matrix completed. So let's just do this on the board, as the presentation is not running as smoothly as oh, there it is. All right, so let's go. So in multiplying this 2 by 2 matrix by our 2 by 1 matrix, we are going to multiply the first element in the first row of the first matrix by the first element in the column of the second matrix. That is going to give us a product of AX. That's going to give us a product of AX. And then we are going to, we are going to add that to the product of the second element in the first row and the second element of the first column. And that is going to give us plus BY. We are going to repeat this for the second row. So we are now going to multiply the first element in the second row by the first element in the column to give us CX. And then we're going to complete it by adding the second element in the second row by the second element in the first column. And that gives us the matrix AX plus BY, CX plus DY. Now, let's just take a quick look back at our matrix that we have established before, which is 2D plus W, 3D plus 3W equal 260, 480. And we're just going to compare them. Are you guys seeing any similarities between the equation that we have written at the start, which is 2D plus W, 3D plus 3W, and the matrix that we just multiplied? Yes, we are seeing some similarities. And what we realize is that the matrix that we just got after multiplying is a 2 by 1 matrix. So we have 2 rows and we have 1 column. The first row consists of AX plus BY, and the second row consists of CX plus DY. Now, in the equation that we wrote earlier, it also is a 2 by 1 matrix where we have 2D plus W being in the first row and 3D plus 3W being in the second row, which means we can now expand this to get 2 more matrices to have it finally in the form of AX plus B. And it would then imply that if we should go ahead to break it down a little bit further, we would have a 2 by 2 matrix being multiplied by a 2 by 1 matrix, giving us the matrix 2D plus W being equal, 2D plus W and 3D plus W. Now let's do a little bit more investigation. We realize that when we multiplied the first element of the first row by the first element of the first column, we got a result of AX, which means for 2D, it must have been that we multiplied the first element of the first row of the first matrix by the first element of the column in the second matrix. So we know that the first element in our 2 by 2 matrix is going to be 2, and we know that the first element in our column has to be D. Now, let's see if we can observe what happens with the product CX. We multiplied C, which is the first element in the second row, by the first element in the first column to get CX. the position occupied by CX is shared by 3D. So it must have meant that we multiplied the second element in the second row by the first element in the column to get 3D. So we know that the second element below 2 would be 3. In a very similar fashion, we multiplied B by Y to get a product of BY, and that is our third element in the matrix. And here, what shares the space or reflects the space of BY is W. Now the coefficient of W here would be 1, which means that we multiplied 1 by Y to get, 1 by W to get 1W. So we know that our third element is going to be 1. And in a very similar fashion, to get dy, we multiplied d by y, which is the second element in the second row multiplied by the second element in the column to get dy, which gives us this product here. So we know that this final element has to be 3. And we know that our final element in the column matrix is going to be W. So what we have now done, we have now been able to identify what all three components, or actually we're going to be going to that now. Let me just skip on to the next slide. Good. So what we have done, we have now identified all three components of our matrix equation. We now have A, which is what we call the matrix of coefficients. We have our X, which is the variable matrix, and we also have our B, which is what we sometimes call the solution matrix, and there are other names for them out there. So don't be too thrown off if the names don't align with what you would have learned so far. So let's take a closer look at these two equations. If we look at the simultaneous equations as is, we recognize that the coefficients of the simultaneous equations is 2, 1, 3, and 3. When we compare it with A, we recognize that all the coefficients are in A, and that is why we call it the matrix of coefficient or coefficients. When we look at our matrix X, we recognize that it has the variables that we are exploring, which are D and W. And then when we look at our matrix B, we recognize that it has the answers, the results to each of these equations, and we call it our solution matrix. So here is what our equation would look like when it's fully in the matrix form. AX is equal to B. Good. So we have been able now to rewrite our simultaneous equations in the form AX plus B. The next thing that we would like to do is to be able now to make X the subject of a formula. Because when we're doing algebra and we are solving for X, we have to make X the subject of the formula. And in this case, we are trying to find the cost of our variables, which means we're going to have to make X the subject of our formula. But before we do that, there are a few things that we want to explore. Let's go to the board. Now, in the previous lesson, we had explored the inverse of a matrix. And we know that the inverse of a matrix is denoted as A to the power of -1. And it is given by the reciprocal of the determinant A multiplied by the adjoint of the matrix A. Okay, now in our case, remember that the matrix of coefficient A was given by 2, 1, 3, and 3. Which means if we are to evaluate this, we'll have to determine our determinant first. And our determinant is given by the product of the leading diagonal, which is 2 times 3, as this is our leading diagonal. And we subtract from the product of our leading diagonal the product of the non-leading diagonal, which is 1 multiplied by 3. So our determinant is going to be equal to 6 minus 3, which is 3. Nice and easy. Every single day and twice on Sundays, right? Good. And then, to determine our adjoint, A, what we're going to do, we are going to interchange the elements of the leading diagonal. So where 2 is, we are now going to put 3. And where 3 is, we are now going to put 2. So what we've done, we've interchanged the elements along the leading diagonal, and then we are now going to negate the elements that are along the non-leading diagonal. And by negating, we simply mean we're going to multiply the elements by -1. So -1 times 1 gives us a product of -1, and -1 multiplied by 3 gives us a product of -3. So we are now going to put these two together to get the inverse of our matrix A. So let me just put it right here. So we are going to say A inverse is equal to the reciprocal of our determinant. And remember, our determinant is 3 multiplied by the adjoint, which is now 3, -1, -3, and 2. Now, I want to ask, what is the purpose of our A inverse? Now, in matrix, we have 3 basic equations that we'll work with in matrices. They are, let me just get this out of the way. Good. They are addition, multiplication, and subtraction. Can anybody, Clive, can you tell me what's missing, Clive? Which one is missing? Which one of our basic operations are missing? Exactly. It is division. We are missing the division, which means in matrix, we don't necessarily divide. Now, what are we going to do if we actually wanted to divide or have the effect of dividing, but we can't divide using matrix? Well, that is what our A inverse helps us to do. It helps us to create the effect as though we're actually dividing. Now, just to bring it home a little bit closer, take for example, we know that in indices, my board is becoming a little bit crowded, but I need these values here. So let's just work with this top portion of the board. Now we know that in indices, if I have 1 divided by A, it can be represented as this fraction here. If I write it in index form, it is the same as A to the power of -1. Now remember, in matrix we really don't divide, but we denote it A to the power of -1 to help us to understand that it gives us the same effect as dividing through by A. Okay, now something else just popped up in my mind, and I am now wondering, what if I actually multiplied A inverse by A? What will happen? So let me have A inverse stay right where it is. And I'm now going to multiply my A inverse by A. And remember, my A inverse is 1 divided by 3, 3, -1, 3, 2, and A, anybody remember what A was? It was 2, 1, 3, 3. So in multiplying these two, remember, we are going to go now row by column. So it's row 1, column 1, that's going to give us the first element in the first column. So it is going to be, let me just write back my scalar right here. It is going to be 3 times 2 plus -1 multiplied by 3. That's going to give us the first element in the first element in row 1, column 1. And then to establish the element in row 2, column 1, we're now going to multiply row 2 by column 1. And that is going to give us 3 times 2 plus 2 times 3 . Oh, this should have been negative here. So this would be -3 here. All right, good. And then to get the element in the first row, second column, I'm now going to multiply row 1 by column 2 to get 3 multiplied by 1 plus -1 times 3. And to get the element that is in the second row, second column, I'm going to multiply row 2 by column 2 to get negative 3 by 1 plus 2 times 3. Don't mind that this gone down in the other part. So we have our scalar. We're going to be simplifying it now. 3 times 2 is 6. Negative 1 times 3 is 3. Is negative 3. We have the product of negative 3 and 2, which gives us negative 6. And the product added to the product of 2 and 3, which gives us 6. We have the product of 3 and 1, which is 3. And we're going to add that to the product of negative 1 and 3, which is negative 3. We also have the product of negative 3 and 1, which is negative 3. And we're, going to add that to the product of 2 and 3, which is 6. We're going to reduce it a little further to get 3, 0. This is going to be 0, and this is going to be 3. And now remember, this is our scalar. Remember, when we have a scalar in front of our matrix, it means that we're going to multiply each element in the matrix by the scalar. And that is going to give us a third times 3 gives us 1. A third times 0 gives us 0. A third times 0 is also 0. And a third times 3 is 1. Now, this looks like something that we've met before. 1, 0, 0, 1. This is the identity matrix for all 2 by 2 matrix. And remember, our identity matrix, when multiplied by any other compatible matrix, it will return the matrix that we multiply it by. Now, you might ask, what do I mean by any other compatible matrix? Now, given that it is a 2 by 2 matrix, we will have to multiply this 2 by 2 matrix by a 2 by 1 matrix or a 2 by 2 matrix, because remember, the number of columns in the first matrix must be equal to the number of rows in the second matrix for the matrix to be compatible. All right, so remember, the identity matrix is the matrix that when multiplied by any other matrix, any other compatible matrix, returns the matrix. All right, so all of these things were necessary now for us to go ahead and continue solving our problems. Okay, so we are now at the step that we're going to make x the subject of the formula. All right. All right. So we have put it in the form ax is equal to b already. And in order to make x the subject of the formula, normally what we would have to do, we would have to divide through by a. Now remember, in matrix we don't divide through, but we have something that gives us the effect of dividing through, which is our A inverse. So we're now going to multiply by A inverse, and we still do that to both sides. So I multiply both sides of my equation by A inverse. Now remember, as we just showed, A multiplied by its inverse gives us the identity matrix. And the identity matrix, when multiplied by its compatible matrix or any other compatible matrix, gives us the matrix in return. So when we have made x the subject of the formula, what we would have realized is that x is equal to A inverse multiplied by b. So here are, let me just state some facts that we would have established already, which is, we first write it in the form ax equal to b. We also know that A is the coefficient, the matrix of coefficient, B is the variable matrix, and x is the variable matrix and B is the solution matrix. The second thing that we know is that we use the inverse to create the same effect as dividing. We also established that in making x the subject of the formula, we multiply both sides by A inverse to arrive at x is equal to A inverse B. Now, some persons may ask, can I multiply the right side of B by A inverse? And I say no. The reason is because, remember, matrix multiplication is not commutative, which means multiplying from the right gives us a different answer from when we multiply on the left-hand side of the matrix. All right. So now that we are at this stage that we have our equation set up to find our variables, we can now substitute A inverse into this equation, this matrix equation here, to now go ahead and determine what our variables are. So we know that x is equal to A inverse B. We know that the matrix X that we were given before was what? DW, which was equal to the inverse. Anybody remember what our inverse is? Oh, it's right there. So our inverse is 1/3, 3, -1, -3, 2. And we're now going to multiply that by B. And remember, B is our solution matrix. And for B, we had $260 and $480. All right. So going forward now, the first thing that we are going to do in simplifying this problem, remember, in multiplying, it is row by column. So we say the first row, and in the second matrix, it's only one column. So it's just the first row by that column. So we are going to have 1/3, 3 times $260 minus $480. And then we're going to have -3 being multiplied by 260. And that is going to be added to the product of $2 and $480. Because remember, we are going row by column. So it is the element, the first element in the row multiplied by the first element in the column. Then it's the second element in the row multiplied by the second element in the column, which gives us this result here. Then the first element in the second row being multiplied by the first element in the column. Second element in the second row being multiplied by the second element in the column. Gives us this result here. All right, good. Now we can reduce these. 3 times 260. So all right, 3 times 200 is 600, and 3 times 60 is 180. We add that together, we get what? 780. We subtract that from $480. And then we also have -3 times 260, all right? 3 times, oh yeah, that would give us -780. And 2 times 4 gives us 960. Is that correct? I hope so. All right. We're going to simplify these expressions. We're going to simplify these expressions now to get 300. And we're going to simplify this one to get, oh, this should be a plus. Okay, good. This will give us 180. Good. So now we're just at the point where we now have to expand where we just now have to multiply by our scalar to determine the cost of one donut and a bottle of water. So now, in order to do that, let me just step across here. It is going to be a third times 300. Now guys, I don't normally advise that we do this, but because of space, I'm just writing the equation straight across. But what I would have normally done, I would have gone down in the other line, rewrite my dw, and then continue working my problem. But we don't have much space working with. So let's go. So it is a third multiplied by 300 gives us $100, and we have a third being multiplied by 180 giving us $60. Therefore, the cost of a bottle of water would be equal, which is W, would be equal to $60, because remember, with equal matrix, the first element is going to be equal to the first element on the other side. The second element in the column is going to be equal to the second element in the matrix on the right hand side. So D is going to be equal to 100 and W is going to be equal to 60. So we now know that one donut will cost us $100, and one bottle of water will cost us $60. Now, if I was doing this here, I would actually write it out. I wouldn't just leave it at D equal. I would write it out. The cost of one bottle of water is 100 and the cost of one bottle of water is 60. But if we leave it here, we can interpret it to be the same, and that is fine. 6 of one thing, half dozen of the other. All right, so let's see if we can look at another question quite quickly. So let me just get this off the board here. All right, so we have 3a minus 2b is equal to 12, and we have our second equation, 2a plus b is equal to 1. Now remember, the first thing that we want to do, and I'm going to show you that we can do this quick and fast. The first thing that we want to be able to do is rewrite it in the form ax is equal to b. Okay, so in doing that, remember a is our matrix of coefficients, so we're going to have 3, negative 2, 2, and when we don't say a coefficient, we know that the coefficient there is 1. So we put 1 here. And then we know that our matrix A is going to be comprised of our variables. So it is going to be A and B. And then we want our equation B, which is simply the solutions, which is 2 and 1. Then we want to rewrite it in the form X is equal to A inverse B, which means we have to determine the inverse of our matrix A. Now remember, the matrix A, its inverse is equal to 1 over the reciprocal of the determinant multiplied by the adjoint of the matrix, which is going to be 1 over the product of the leading diagonal, which is 3. Sorry, this should be 2. 1, 1. Okay, good. So which is 3 times 1, which is 3. Take away the product of the non-leading diagonal, which is going to be negative 4. And we multiply that by the adjoint. Now remember, with the adjoint, what we do, we interchange the values along the elements along the leading diagonal. So this becomes 1 and this becomes 3. And we negate the other 2 that are along the non-leading diagonal. So negative 1 times negative 2 gives us 2. And now this becomes negative 2 also. So we now have our A inverse. So all that's left for us to do now is multiply. To determine the values of A and B is multiply our inverse, which is 3 minus 7. Sorry, 3 minus negative 4 gives us 7. And this is going to be 1, 2, negative 2, 3, being multiplied by 12, and 1. Now, we are going to go row by column, and going row by column, we would end up with 1 times 12 gives us 12. 2 times 1 gives us 2. Then we go negative 2 times 12 gives us negative 24. And 3 times 1 gives us 3. We can further simplify this. Sorry, let me just go up here to get 1 over 7, 14, negative 21. And when we divide through by 7, we see that what we'll end up with is 2 and 3. We end up with the column matrix 2, negative 3. So we know that the value of A is 2 and the value of B is equal to negative 3. Well, guys, it's a mouthful as always. I hope you would have learned. That's all for CSEC mathematics today.